Hello everyone, it's a balmy Friday afternoon here and it's the perfect time to talk about area. But first I want to quickly review the relationship between length, area and volume, and then we'll get stuck into it. So first of all, length. Length is most commonly we know as distance. It's the distance from here to the door. It's the distance along the top of this chair if I measured it to be about 40 centimetres or so. It's the distance from Tamborine Mountain to Canungra. Right? It's a length, it's one-dimensional, it's a distance. So length is measured in one dimension. Area, on the other hand, is when we start talking about surfaces, like the surface of this board here, or the surface of this table that everything is sitting on that you can't quite see, or the surface of the floor, how much floor covering would be needed in a room. At that point, we're talking in two dimensions. There's a length and there's a width. Area exists in two dimensions. Volume, when we start talking about volume, we start talking about, well, how much tea is in this cup, or how much water is in a dam, or similar. We're starting to work, or how much I can put in the washing machine that's working back there. We've got length, width and height. We're starting to work in three dimensions. Volume exists in three dimensions. Now that might seem like a moderately obvious observation, but it's really useful when we think about the mathematics of converting between units, which is what I'm about to talk about briefly. So usually for measurement, we see millimetres, centimetres, metres and kilometres. I'm now going to draw funky arrows on here. We're going to make the worm to remind ourselves how to convert between all of these units. So here, general rule, when I go to a bigger unit, it'll be a smaller number. Right? How many millimetres is in a centimetre? I hope you recognise there's 10. But when I go to a bigger unit, it will be a smaller number. So if I go in this direction, I'll divide. Bigger unit, smaller number. How many centimetres are in a metre? 100. So we divide by 100 going there again. Bigger unit, smaller number. How many metres are in a kilometre? Hopefully you tell me 1,000. Bigger unit, it'll be smaller values. On the other hand, going back in the other direction, it's always we're going to a smaller unit, so it's going to be a bigger number. So this will be multiplied by 1,000, multiplied by 100, and multiplied by 10. Now, that's length, right? When we talk about, this pen might be 12 centimetres long, we're talking about length. What if we were talking about area? How does this diagram change? I'm going to do a magic trick and pause and magically change it into an area diagram. Now we're talking about area. What have I done? Well, we're now dealing in square units. So it's millimetres squared, centimetres squared, metres squared and kilometres squared. That tells me from the start that I'm dealing with an area rather than a length or a volume. I know I'm talking about a surface now, a two-dimensional surface. These are units of area. And all I've had to do to conversions is square them. Every single one of them just gets squared. And that's how you can convert between areas of units of area. Now, do you want to have a guess what it looks like when I start dealing with volume? I'm going to do a magic trick again. And there it is. We're now in units of volume because I can see millimetres cubed, centimetres cubed, metres cubed and kilometres cubed. So this is telling me that we're now working in volume. And what's happened to all our conversions? Well, now they're to the power of 3 instead of the power of 2 or 1. So that's it. For volume, we have cubed units and our conversion numbers are to the power of 3. But today we're talking about area, so I'm going to quickly magically return to area. And there we are. We're back to area. We're going to do a quick couple of examples of converting between units of area. So let's do 8,274 millimetres squared into something centimetres squared. Right, so normally millimetres to centimetres. How many millimetres are in a centimetre? 10. It's a bigger unit, so it'll be a smaller number. And lastly, we're dealing in area. The units are squared. So I need to divide by 10 squared which is 100. If I divide by 100, we're going to move the decimal place two figures, and we're going to get 87.74. All right, a second example I'll do here quickly is if I had 4.37 meters squared and I want to change that to centimeters squared. All right, this time what's the conversion? There's 100 centimeters in a meter squared because we're dealing with area. And I'm going to a smaller unit, so it'll be a bigger number. I'm going to multiply. You may want to check what 100 squared is, 100 times 100. I know that's going to be 10,000, essentially because if you multiply 100 by 100, that's 4 zeros in the question. There'll be 4 zeros in the answer. That's how I did that quickly in my head. Right, if I multiply that by 10,000, you're going to end up with 43,700 centimetres squared. Right, so that's a quick review of the relationship between length, area and volume, and the unit conversions, and a couple of examples of area unit conversions. What I now need to do is revise with you, and there's quite a few objects I actually need to revise. You've probably done almost all of them before, but we need to do the area of 9 different objects. So I'm going to rip through reviewing how to do the area of 9 different objects now, starting with some of the simpler ones. So, here we go. Object number 1 is our old friend, the square. Alright, so number 1, square. So I'm going to give you a picture. A square, of course, has all sides the same, and often we call the side length L. And for an example, I'm going to make that length 8 centimetres. There we go. Now, do you remember the formula for area of a square? It's similar to a rectangle. You might remember a rectangle being length times width. Well, with a square, the length is always the same, right? Length here times length. It's just length times length, which we can write as L squared. In our particular example, if we say that the length is 8 centimetres then, it gives us A is 8 squared, which is 64. The units being centimetres squared, because it's units of area. All right, if you wanted to think about that logically, if that sort of thing phases you a bit, could you imagine splitting this into 8? 3, 4, 5, 6, 7, 8. If I split that into the 8 centimetres and did the same in the other direction, 2, 3, 4, 5, 6, 7, 8, how many little centimetre squared blocks would I have in there? I'd have 64, wouldn't I? I'd have 8 times 8. It makes sense when you sit down and, draw little grids on it, but we're probably a bit past that now, and I don't want this video to go over 20 minutes if possible, so let's keep going. Now, I just mentioned rectangle. I'm going to do it in a little more detail. So here's a rectangle. This side and those sides are the same length, and normally we call this L for length and this W for width. And in my example, I'm going to call this 8.3 millimeters. I'm going to call this 4.3 millimeters. All right, I'm going to need a calculator for this, so I hope there's still one in my bag. Yes, there is. That's a good sign. All right, now you may remember the formula, and by the way, I don't do this for decoration. Every time you do a question in this area, in any area in maths now, I expect you to write the formula first. So in this case, you should remember that the area of a rectangle is length times width. Secondly, I expect you to put the values in, 8.3 times 4.3. And finally then, I expect you to give the answer. So I put that in the calculator, and I get 35.69, and we're in millimetres squared. All right, that's 2 objects down, so a mere 7 to go. Hope you've got that down because I'm about to clear the board. All right. All right, so third object is a triangle. You've done them for a while. And the biggest trick with triangles in terms of what we've done so far, and we will advance this later in the year, is you need the perpendicular height. So along here is the B for the base, but you need the height that is at 90 degrees to the base. You need this perpendicular height. That's the one at 90 degrees to the base. So that there is our H for the perpendicular height. For this example, what are we going to do? I'm going to do 4 metres and 6 metres in this one. Do you remember the formula for area of a triangle? Maybe, maybe not. Area is 1/2 base times height. There's a second way of writing that if you want. You could just write it as base height divided by 2. It's exactly the same thing. I might actually show you it that way because it's a little bit cleaner. I'm only writing one line on it and don't even have to write the 1. So in this case, the base was 6, the height was 4. Put it in our formula. 6 times 4 is 24, divided by 2 is 12 metres squared, because we're dealing with area. You can actually, if you're feeling inventive, look at a triangle as being half a rectangle. Can you picture the rectangle? It's really half of a rectangle. The formula, in effect, is half of that rectangle, half the length times width, if you can see it. A few of the objects are like that. You're in for some surprises. Object number 4 is a parallelogram. All right, so here I've got 2 parallel sides. So the symbols are, that one's going the same direction and that one's going the same direction. Similar in concept to before, they call this here the base. You need the perpendicular height again, so at 90 degrees to the base. We need the height. And if you've got them, it's actually just the base times the height. Why? I'll give you some logic. What if I drew those lines in place? If I took this triangle here, it would fit perfectly in there, wouldn't it? If I took that triangle there and dumped it there, what object would I create? It'd be a rectangle, wouldn't it? So really the area is just the length times the width, except we've called it base and height. Cut that story short. Area of a parallelogram is simply base times height. So let's call this 3.7 kilometres, and I'm going to call this 2.9 kilometres. So if I have area is base times height, it's going to be 3.7 times 2.9. I put that in a calculator. And it gives 10.73 kilometres squared. So that, wonderful people, is object number 4. Please take it down. I'm going to have to knock all that off. All right. 5 objects to go. So, object number 5 is a trapezium. So those are things that have parallel lines at the top and bottom and some sort of connection in between. The formula for this looks daunting. but I'm going to also explain to you how you can get that formula in case you're curious. So they call the length along the bottom A, the length up here B, and the perpendicular height, again it has to be at right angles, I call that H. Now, what you've got to think of is, remember the area of a rectangle is length times width? Well, what length should you use there? What the formula does is it averages A and B. So if I wanted the average value of A and B, I'd add them together and divide them by 2. Right? That would give me the average value between A and B. That sort of gives you an average length, and then you can just multiply it by the width, like you would with a rectangle. So the logic I'm saying is that with a rectangle, you do use area as length times width. But for this object, the length needs to be the average of A and B times the width, which is, we've labelled H in this case. All right, so that's the length in this thing, and that's the height. Now you simplify that, and you'll see the formula in your book. Another way of writing this is simply 1/2 A plus B H. That's the formula you see in your book. That's simply another way of writing what I just written there. All right, that's what you need to be able to use. If everything else I said was ridiculous to you, don't worry about it. That's the formula you need to use to find the area of a trapezium. So let's put some values down here. I'm going to call that 3.8 centimetres, 7.9 centimetres, and 3.2 centimetres here. So I've got to put all those values in the formula. It's going to be big. A is 7.9, B is 3.8. Remember, where there's no symbol, it means multiply. The height is 3.2. That's a bit to put in the calculator, but we're going to do it. So we go 0.5 times, in brackets, 7.9 plus 3.8 times 3.2. Put it in our calculator, just checking I've written all that down right. And it gives us 18.72 centimetres squared. All right, that's object number 5. Object number 6 is a rhombus. All right, rhombus is a square on its side. It looks a bit like this. All sides are the same length. All right, and what they do for the formula is they say that's x, the other diagonal's y, so they label the diagonals x and y, and then they tell you that the area is simply 1/2 xy, which you could also write simply as xy over 2. Alright, so if I said that x is 7.2 metres and y is 4.1 metres, we could substitute the values in. X is 7.2, y is 4.1. Put the values in the formula. So 7.2 times 4.1 divided by 2. You'll get 14.76 metres squared. Now, again, if you've got a bit of vision here, this thing is actually half of a rectangle. I'll show you how. That triangle's the same as there, that one's the same as there, that one's the same as there, and that one's the same as there. And look what you've got. X is like the length and y is like the width. A rhombus, if you look at it the right way, again, is half of a rectangle. Isn't that cool? Like a triangle was. It's really half a rectangle. Anyway, that's for your enjoyment, but not critical. You've got to remember mainly that, look, it's x, y, the diagonals multiplied together divided by 2. Now, I'm going to run over time here, so I'm just going to knock this off and keep going with object 7 now. Right, object 7 is a kite. Right, so where's the purple? 7. kite. Kite looks like this. And that length is the same as that, and that length is the same as that. This formula looks pretty well identical to the rhombus. XY, actually they put it the other way around, not that that really matters. Alright, so it's essentially the corners again. Y is the height from the top to the bottom, X is the distance from the left to the right, and the formula again is area is 1/2 XY, which you can also write as simply XY on 2 if you want. Alright, so in this case, if I made this 7.7 millimeters and I made this 12 millimeters, you put the values in the formula, so area will be 7 times 12 divided by 2, which will give you 7 times 6, 42 millimeters squared. There's your area. Now, like the rhombus and the triangle, if you look closely, you can realize that the kite is actually half of a rectangle. I'll just show you that quickly. If I draw a little line around the outside here. And a line through there. That triangle is the same as that. That triangle is the same as that. That triangle is the same as that. And that triangle is the same as that. Again, you can look at it as being half of a rectangle. So it was always going to be half of our 12 times 7, half of XY. Cool, huh? Object number 8 and 9 are actually linked, so I'm probably going to knock this off and start on a new screen now for 8 and 9. Alright, object 8 is a circle. So with our circle, we had a radius, and you may or may not remember D for diameter. The formula doesn't use diameter, I'm just reminding you that a diameter is all the way through and radius is half the way through. The formula for the area of a circle is, of course, pi r squared. Let's say the radius here was 4.2 kilometers. It's a very, very large crop circle. Alright, so it's going to be pi times 4.2 squared. We put that in our calculator, pi times 4.2 squared. And we're going to get our approximately, so I need to use the wavy lines. Whenever we involve pi, we start to have to round the answer at the end. So it's approximately 55.42 kilometers squared. That's a large amount of land. The last item here is a sector. Now there is a nice section in your book that goes through this. A sector is part of a circle. So, you know, I like to draw something like a Pac-Man here. That's terrible. Oh. And I might make that. That's what we call theta, the angle that's within it. I might call this one 920 degrees for the purpose of our example today. And we also have a radius, and in this case the radius I will make, we'll just make it 2 meters to keep it interesting. Look, the area, if you think about it, is a proportion of the full circle. And there's a nice activity deriving this formula in the text if you want to follow it, but I'm running way over time, so I'm not going to do it right now. How many degrees are in a circle? Hopefully you know it's 360. So it's essentially the proportion of the circle, meaning pi over 360 degrees, that's how much of the circle is in this, multiplied by the normal area formula of pi r squared. So in this case, it's got a full 290 degrees. It's almost a full circle, isn't it? It's not far off. It's going to be 290 divided by 360 times pi times the radius squared. And the radius was 2. So if you put that in your calculator, 290 over 360 times pi times 4, and you get something a bit like that. It's going to be approximately equal to 10.12 meters squared, because we're still dealing with area. There you go, guys. Massive 9 objects, area of 9 different objects. Have fun, enjoy. Remember to show you're working out. Formula, substitution, answer. Cheers.